Good morning. Welcome to today's webcast, Reshaping Reservoir Management, using direct measurements of phase flow for enhancing field production. I'm Ivy Diaz, digital editor of World Oil, and I'll be your moderator today. Discover how innovative chemical tracer technology is reshaping reservoir management and field optimization. This webcast will highlight low-risk, non-intrusive, non-wireline-deployed tracer advancements that provide essential insights into short and long-term phase production and interwell communication. These solutions enable operators to improve well performance, establish best practices, and drive strategic field development, all without costly or disruptive interventions. Joining us for today's webcast are Mariano Clerici-Garrico, Global Technology Manager, and Patrick Hayes, Business Development Manager, North America from Tracero, and Mike Gerstner, owner of Gerstner Petroleum Services. Mariano was born in Buenos Aires, Argentina, and has over 25 years of experience in the oil and gas industry, having worked in companies such as YPF, NOV, Nalco, plus Petrol, amongst others. He's an industrial engineer with a postgrad in oil and gas production and a degree in reservoir engineering. He's mostly worked with water flooding and enhanced oil recovery projects, although during the last 4 years, he's focused on surfactant use in unconventional fields in the US and Argentina. Mike Gerstner is the owner of Gerstner Petroleum Services, and he specializes in stimulation design and completion optimization. He's been in the industry for 40 years and has worked at BJ Services as the Permian Sales Manager, Baker Hughes as the Geomarket Sales and Engineering Manager, and CUDD Energy Services as the Sales and Operations Manager. He's co-authored several SPE papers on stimulation fluids, completion techniques, and specialty proppants. Mike has a Bachelor of Science degree from Texas Tech University. Patrick Hayes is Tracero's Business Development Manager for North America. Having joined Tracero in 2004, Patrick has proven his expertise in chemical tracer technology by managing global multidiscipline projects with a focus on improving operator efficiencies and increasing customers' return on capital investments from upstream through to downstream industries. While working in the North Sea, Europe, Middle East, and parts of West Africa, Patrick's innovative approach to applying novel measurement technologies has helped customers gain additional insight into the different aspects of the hydrocarbon production cycle, from subsurface to midstream through to downstream refining. Patrick is now focused on working with operators in North America to help them gain production efficiencies through the better understanding of the relationships between reservoir characteristics, completions, and production. So we welcome our speakers today. For now, just a few general housekeeping notes before we get started. Following the presentation, we'll be having a short question and answer session. You can participate in the Q&A session by asking questions at any time during the presentation. Just type your question into the Q&A box located on the bottom left corner of your screen, and then click the submit button. Please take this time to familiarize yourself with the webinar platform. At the bottom of your screen, there are several application widgets you can use. All the widgets are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can enlarge the slide window at any time by clicking on the arrows in the top right corner of the slide area. The slides will advance automatically through the event. And lastly, if you're experiencing any problems with the program, please press F5 on your keyboard and it'll refresh the presentation. You can also visit the webcast help guide by clicking on the help button below the slide window. And now I'll welcome our speakers and we can go ahead and get started with the webcast.
Good morning to everyone, and thank you for the kind introduction to the webinar. Today's webinar is about taking advantage of direct measurements of phase flow and enhancing field production. We as a team will cover interesting applications and case uses of the chemical tracer technology that everyone can take advantage of in the oil industry, as well as those working in the subsurface. We have included case studies that involve unconventional applications and projects production management, the use of solid controlled release tracers in combination with liquid uses for EOR. Myself and the team are excited to get the presentation started. Before we get too deep into case studies applications, it's very important to have a full understanding of what makes an effective chemical tracer compound. In order to do this, we have to look at unique chemical properties of the compounds as well as characteristics that they must have. Let's get started with chemical properties. One of the effective chemical tracers is one, it has to be foreign to the reservoir environment and not naturally present. This way, we are identifying the presence and concentration of one or more man-made unique compounds upon recovery. The non-native component ensures no confusion with any type of possible native mineralogy or DNA, and confirms the origination of the material being measured. The subsurface environment is a harsh environment. It can have high temperatures, high pressures, and extreme mineralogy full of metals, chemicals, and bacteria. The tracer used must be robust and virtually inert in the subsurface environment. The tracer need to not interact with the geology or the chemicals injected during the specific application. These are all equally important. The non-absorbent nature of the tracer to not interact with the rock, not degrade over time, and stay with the intended phase is critical to getting not only qualitative data, but quantitative data, but achieving quantitative results for individual phases of recovery. All of the above must be achieved as well as tracers being easily detectable. Today, many tracers are identifiable and quantifiable in parts per trillion, and some to the quadrillionth. That's 10 to the minus 18 somehow. Something that sets quality of tracers apart from one tracer provider to another is the tracer provider's criteria for the phase-specific nature of tracer. Chemical tracers that are intended to stay with the intended phase in the reservoir conditions must all have the same minimum partitioning characteristics and not be adjusted by calibration with subsurface environments. A tracer must have little to no toxicity, be safe for transit, be safe for handling, all while maintaining economic viability for use. The physical forms of tracers are not usually considered by many end users, and this can have unintended consequences, ultimately impacting goals and objectives, making for inconclusive conclusions and sometimes even misleading results. The manufacturing and physical state of tracers applications will dictate if the tracers are quantifiable or qualitative, even if the correct chemical characteristics are taken into consideration. This means that we must be careful when selecting not only tracer chemicals, but also the physical forms of the application. The left two pictures represent two types of solid tracer materials. One that is a particulate and the other are bars attached to the lower completion. Solid tracers that are not absorbed but manufactured can have a linear release. Tracer uses patented methods of encapsulation and formulation to create longevity over time. Longevity of release are tricky business in the subsurface environment, as you must have enough tracer release to detect the tracer in the cumulative phase flow, but also so little it lasts a long time. However, both particulates and solid bars cannot be quantified under steady state producing conditions, as they can produce the same tracer result when under opposite flow conditions, such as low flow and high flow. This makes solid tracers a binary yes-no outcome under steady state flow conditions. In specific circumstances, A transient study can be used to quantify the flow. Liquid tracers are a great tool for quantifying flow in their specific phase. This application of chemical tracers for quantification and characterization of injected and recovered fluids is decades proven. Very often used for the quantification of recovery, sweep efficiency, and characterization of injectors to producers for enhanced oil recovery. The most common mistake when analyzing liquid and gas tracer recoveries is only focusing on the concentrations recovered without adding the volumes to the equation. The masses recovered are related to the placement and production from stage or groups traced. Tracerco's patented applications for hydrocarbon tracers injected during stimulation has provided proven unmatched accuracy for wireless surveillance and quantification of hydrocarbon production over time. The far right presents partitioning tracers. Now, with added innovation from experience and expertise, Tracerco has developed its tracers lists to include tracers that are used to quantify remaining oil saturation in both interwell and single well testing by adding passive phase specific tracers and those that partition into the hydrocarbon phase and can be quantified during recovery to provide remaining oil saturation measurement. With that, I will hand the first series of case studies over to Mike.
Thanks, Pat. Hello, I'm Mike Gershner with Gershner Petroleum Services, and I'm the Tracerco technical representative for the Permian Basin in South Texas. This area includes southeastern New Mexico, Midland, Odessa, San Antonio, Austin, and Corpus Christi. I'm going to present 3 unconventional case studies pertaining to how tracers are used for flow assurance, landing zone considerations, and operational management. For the first case study, we will look at 2 horizontal wells on a single pad where tracers were used to determine if there was flow along the entire lateral. In many instances, there can be obstructions in the wellbore due to sand that has flown back into the lateral, or in this case, the tracers were used to determine if the dissolvable frac plugs had actually dissolved. The graphic at the bottom of the slide shows both wells along with the stage numbers in a horizontal view. One well had 70 stages and the other 71. Both wells were completed with a zipper stimulation, adding individual water and oil tracers into every 4 stages. Both of these wells used dissolvable plugs in stages 1 through 30, and composite plugs were used in the remaining stages. After the stimulation, the composite plugs were drilled out, but all remaining dissolvable plugs were left in the wellbore. The well was shut in for a very short period of time and then placed into production. So this next slide is a bar chart for the first well, and it shows the allotted production across the lateral after catching flowback samples and analyzing them for individual tracers. Each bar chart is plotted against the wellbore path with the different colors along this path illustrating the change in the gamma ray, which is at the bottom. The gamma ray legend is in the top left corner of each plot. The bar chart in blue shows the cumulative water production for each stage, with the lower green bars illustrating the oil production per stage. Looking at the top chart, it is evident that there's no production coming from stages 1 through 30. This is where the dissolvable plugs are located. The well has a bottom hole temperature over 200 degrees Fahrenheit. The operator decided to go back into the well and drill out the remaining dissolvable plugs. The lower chart shows production after the drill out. It's obvious that there's substantial production achieved after the obstructions were removed from the wellbore. The second slide is on the second well on that same pad. Once again, the top chart shows that stages 1 through 30, there was virtually no production coming from this area. The operator drilled out the dissolvable plugs that were in stages 1 through 30, just like the first well. As illustrated in the bottom chart, the well was placed back on production and a significant increase in production was achieved. Both of these wells show how tracers can be very effective in identifying blockages within a horizontal wellbore. Now we'll go to case study number 2, where we will look at tracer data to see how formation barriers impact production along a horizontal well. Case study number 2 is a horizontal well in the Permian Basin. The stratigraphy is a series of anhydrite and dolomite producing zones where the anhydrite was believed to have a higher stress value, which would force fracture treatments to grow down. The well was completed with a 48-stage cross-link treatment with the operator's objectives to examine the production variability of the lateral while using tracers. A single unique oil and water tracer was injected in every 2 stages. So this well is in the Central Basin platform of the Permian Basin. The illustration on the left shows the San Andres, which is in green, and where it is located in relation to other formations. The illustration on the right shows the Central Basin platform, which is outlined in the center in a darker shade, and it shows the various San Andres fields scattered throughout the basin. The cumulative oil production per field is in the legend to the right, with the lighter color representing the smaller cum values and the corresponding darker colors showing the increasing cumulative values per field. On this slide, the left shows the layering of anhydrite within different producing zones. Anhydrite is represented by the darker shaded color, with the dolomite layers in white, which are layered in between the anhydrite. The anhydrite is sometimes layered in stringers throughout these zones, and they can be unpredictable in their deposition. The figure on the right is a seismic representation of the anhydrite and dolomite layers, illustrating the layering of the formations with the variability in deposition throughout the zones. On this slide, the bottom half shows the oil production. This is just oil production, which is in green. The upper half of the plot shows the drill path with an anhydrite layer at the top and the producing dolomite section below it. Through stages 21 through 36, the path begins to rise along the lateral, as illustrated by the red oval in the top diagram. Looking at the production at the bottom in stages 23, 24, 27, 28, 31, and 32, there is no oil production coming from these zones. It's on the bottom part of that chart in green. Stages 35 and 36 show some slight oil production initially, and then both stages drop to 0. This bar chart is of oil production versus the gamma ray, which is in the different colors along the well. The dashed green bar is the cumulative oil production per stage after 3 months, with the solid green bars illustrating the production at the end, the daily production at the end of the 3-month time period. The 4 arrows show where the well contacted an anhydrite barrier towards the top of the producing zone. These 4 zones did not produce any oil after 3 months. It was assumed that the barrier would stop the height growth of the frac job and force the fracture to grow down. Instead, the fracture grew upward and did not place any proppant into the producing zone. The operator realized that the drill path on subsequent wells would need to be placed far enough away from the anhydrite barrier to keep the prop fracture in the productive dolomite interval. For case study number 3, we will look at using tracer data for operational management of well production. This well is a horizontal conventional well in the Permian Basin in an area where there are multiple operators injecting produced water into disposal wells. The well was completed with a cross-link system in 36 stages. Unique oil and water tracers were pumped into the toe and heel, and the rest of the lateral used one unique oil and water tracer every 2 stages. The operator's objective was to examine the production variability using tracers. This line here is a bar chart of oil and water produced 30 days after the well was completed and placed on production. Unfortunately, the well produced no oil as represented by the blue bars, which is the water production. This was extremely unusual for this formation and was not representative of multiple other wells that were completed in this zone. After examining the tracer production data, it was evident that the vast majority of the water was coming from stages 1 through 24, as represented by the larger bars, with a much smaller volume coming from stages 25 through 36. Based on the quantification of the tracer data, the operator decided to set a bridge plug between stages 24 and 25. As the slide illustrates, the production from stages 1 through 24 was shut off. On stages 25 through 36, the blue bars are the cumulative water production and the green bars are the cumulative oil production. Oil production on this well jumped to 1,200 barrels of oil per day. It was evident that the fracture treatment had intersected an injection system within the area. The operator was able to set a bridge plug, cut off the high water producing intervals, and make significant oil production from the stages close to the heel. Now I'll turn this back over to Pat for case study number 4.
Mike, thank you for sharing those interesting case studies and how chemical tracers can provide big returns from low-cost, simple tracer additions for flow assurance application. Then how applications can help with more complex problems, solving reservoir development strategies and production operations managed using chemical tracer data. These are all powerful outcomes from tracers without intervention by collecting a simple sample. So now we'll move on to case study 4. When answering specific questions involving subsurface production behavior over time, it may be required the use of multiple phases of tracers, as well as multiple forms applied at different times of the stimulation, field development, or operations. Case study 4 contains case examples where the evaluation of multiple variables was being investigated to understand fluid behavior, proppant transport area, a long-term production associated with the maximum frac length, longer-term production fractures, and impacts on offset interactions. Slide 19 for the 2 pads that there are part of case study 4. The tracer applications consisted of using liquid tracers applied for water and oil phases for the purpose of quantification in different sections of the lateral, observing production related to geology, well length, as well as offset wells. Some offset parents were involved, and others were additional child wells sampled and completed at the same time. Absorbed solid particulate tracers were applied to evaluate the difference in performance to the liquid tracers that are quantifiable, and compared to controlled release encapsulated materials used for longer term recovery. The controlled release materials were applied for the water and oil phases to determine longer term prop fracture communication for the oil and water phases. The solid tracer particulate size was 4070 mesh. Although these results would be binary for the solid materials, these would provide significant data when correlated to the initial quantified liquid and water phase traced. Pad 1 is where we'll start. Pad 1, as previously mentioned, understanding the data from different physical forms was imperative to acquiring the information to meet goals and objectives. Though not always intuitive, in this pad, both liquids and solids were used to determine communication, production, and stimulation impacts that may over time change. 2 wells were traced using absorbed solids, manufactured solids and liquids for the water and oil phases. Pad 1's results, liquid water tracers versus absorbed and manufactured solids. On the right, we present the line graphs, the data from one of the traced wells on the pad. The tracers recovered from the injected well is provided in the far left, representing tracers over time with higher volumes initially on the left and reducing over time to the right. The subsequent boxes indicate the offset well results in each box, with early samples on the left and progressing over time to the right. The top trace in blue is the water tracers applied during the stimulation at a fixed concentration over time. This gives a direct correlation to stimulation fluid recoveries and communication. The completions fluid tracing indicated higher levels of communication with offsets that decreased steadily over time and quickly transitioned to reservoir fluid being a more dominant portion of the flow. The absorbed oil tracer materials samples recovery indicated large masses at offsets that than those produced from the injected well over time when compared to those results from the controlled release material. Spikes in concentrations were observed from the absorbed material applied. These could not be correlated to increases in volumes produced due to the binary results and did not trend with the stage quantification of the liquid oils used that quantified stage production. Controlled release tracers that were applied indicated predominant production over the long term at the traced child well, with some communication to the offsets that quickly declined. This is presented in the green trace at the bottom plot. The second pad, 2 wells, were traced using oil and water solid and liquid tracers. No absorbed tracers were used in this study. Tracers were applied at different times during the stimulation to look at potential production differences along the lateral, as well as different sections of the stimulated parts of the proppant pack. Liquid tracers were used to quantify associated production of water and communication relating to the amount of completion fluid communication over time with offset wells. The slide indicates the water tracer results from the utilization of both the liquid water tracers and the solid controlled release water tracers. The controlled release tracers were applied in the well on the left. The results presented in time from left to right. The subsequent box to the right is the offset wells results, again with the orange tracer from the controlled release and the blue for the liquid tracers. The blue trace represents the completions fluid traced at a steady state concentration over time with the stimulation, and the tracers recovered in the production from the stimulated well and that of the offset. The higher concentration recovered from the controlled release material suggests more tracer potentially remain near wellbore in the proppant pack. The decline rates observed far field from the liquid water versus the proppant material were very similar. This tracer also may be associated with the transfer from the stimulation fluid itself. The liquid oil tracers, represented in orange trace, and the controlled release, represented by the green trace, indicated offset well communication at a much lower level than either of the water tracers. However, recovery of tracer from the injected well were much lower from the controlled release tracer, indicating the function of the controlled release material and the location of contact are affecting the release rates from the solids with mobile oil near wellbore. Liquid oil tracers did indicate a small amount of communication that could be quantified with the offset during early production, not indicated by the controlled release proppant material. Absorbed material tracers indicate recoveries in like that of liquid completion fluids regarding communication, but in this case had variable profiles that did not resemble either liquid trends or controlled release trends. Produced tracer concentrations of absorbed materials did not correlate to the production rates observed. Pad 1 controlled release mass tracer recovery was much lower than the liquids and absorbed materials, indicating the function of the controlling encapsulation process of the beads. Liquid tracers remain the only way to effectively quantify phase production over time under steady state by combining phase production, volumes, and concentrations. Solid materials, both absorbed and manufactured, were not effective at measuring total hydraulic stimulation communication that was accomplished with liquids, but did indicate reductions in observed communication to offsets for both water and oil phases that may better represent proppants. Controlled release manufactured materials significantly reduce the total tracer release over time and provide a longer-term monitoring method for production and communication under binary measurement conditions. With that, I'll hand the presentation over to my colleague Mariano to present the latest well management and production for EOR.
Thank you, Patrick. My name is Mariano Clarici. I'm the Global Technology Manager for TracerCo. So thank you, everybody, for joining us today. I'm going to be talking a little bit about the interwell technology, basically, for water floods, EOR projects, IOR projects. This is a very traditional, and I would say our mostly used technology, maybe over 30, 40 years of tracers being used for these kind of projects. So I want to get into some details explaining the importance of this technology to understand reservoir and water flow in the reservoir, especially to improve the oil recovery. This looks like a very simple image, but it has a lot of information on it. Basically, what we do is we inject a pulse of tracer, and the results we get from the lab, understanding how that tracer has moved through the reservoir, gives us a lot of information. So in here, you can see that obviously 2 of the wells did not see the tracers, but the other 2 wells obviously did. You can see it in one case, we have a curve with a very big peak and a short curve, and the other ones have a more flat out curve with a lower peak. Basically, with that information, what we can interpret is if we're having a good sweep efficiency in the reservoir and how much volume of rock we're contacting with that injection water. So in this case, you can really understand where you need to improve, right? And the times. We have two very important data points here. We have the breakthrough time, which is the time that it takes us to detect the tracer at the producing well, and the mean time, which is the average, or let's say the curve that the tracer data gives us. So with this information, we're able to take proper decisions on what our efficiency problem is in this field, or this reservoir, or even this pattern, because it could actually change in the same field. So what we're looking for is obviously the breakthrough time. The shorter it is, the more of an issue that we have. So normally in the industry, there's different ways of evaluating this, but usually if it's 90 days or less, it's considered that there's an issue, or a sweep efficiency issue, or channeling issue in that part of the field. And obviously the amount of tracer we're recovering. So if the breakthrough is short, and we have that curve, that we have that peak like the one on the lower left, it means that we have a very small sweep efficiency in this area. So basically we're connecting through a very small pipe, to have something more visual, the injector to the producer. The longer the tracers take, the better it is, the more we're sweeping. And obviously the tracer cum value is also important. We want to try to recover the least amount of possible. So it's telling us that it's contacting the most amount of rock. It's pushing that oil towards the producing well. So obviously you can see we have a ton of calculations that we get from all this data. Everybody can understand where we're going with this. And what I always try to highlight is it's the only concrete information that you have, correct? Why is this important? Because it's all this data can go into your simulation software. You understand how much you're really sweeping, how much you're really contacting, and you can detect. I mean, maybe you have a very big efficiency sweep, but you're not producing the oil. So then you can detect if it's mobility issues. There's a lot of information, and it's the only technology that travels through the reservoir. It gives you hard data. I always highlight this. Hard data is critical to make these decisions. You know, simulations are great. You can have a lot of information, but the tracer data helps you adjust that information, or that simulator, and put it into a proper perspective to make the proper decisions after that, right? If you have to go to gel treatments, you know, conformance, if your EOR projects, your polymer flood is the right way to go, if it's a problem of near well bore, you know, all these situations are going to be clear once you have the data from the tracer. And in most cases, you can allocate this kind of information to nearby wells, right? So it's very important to design the treatment that you're going to do, the tracer treatment, to figure out how you can get the most information out of your field, correct? And like Patrick was already saying, I don't want to go into too much. He started out with this. We have the qualitative and quantitative data. Obviously, the more detail we can get, we can measure all these efficiencies or improvements that can be done in the field. There's tons of cases. Obviously, we can do tracers by layer or just by well. It depends on what you're interested in understanding and getting from the data. So obviously we can go into a lot more details. Please reach out to us and bring us your cases. We'll have you, we can present to you all the information that we have, tons of cases that we've done. We have done hundreds and hundreds of these projects worldwide. Like I said before, it's probably one of the oldest technologies for tracer, always used in interwell since the 50s and 60s that there's been projects worldwide. So this is very sophisticated and very advanced. the lifetime of the tracers is not an issue. We have wells that we've been measuring over 10 years. Later down the line, we still see them. We do offshore projects, we do onshore projects. I mean, it's a technology that's capable of any field that can be, that is required. So back to you, Ivy. Thank you, everyone.
Hi, so sorry everyone, my screen froze for a moment there. Thank you all for that great presentation. We'll now transition to the question and answer portion of our webcast. And audience members, you can continue to submit your questions in the Q&A box located on the bottom left corner of your screen. So now let's start with our first question. Could this technology be applied in the underground gas storage project?
I'd be happy to take that question. Hello, Ivy?
Yes, I'm here.
Sure. Thank you. All right. You know, chemical tracers are a fantastic way to be able to quantify not only what's being injected and produced from offset wells, but it's also a great technology to be able to quantify what's being recovered from the injected well itself, say under huff and puff scenarios, if there's concerns about losses during gas storage environments, things like that. And then, of course, if the gas is moving to unintended locations, either structures, you know, shallower formations and being produced with offsets. So it's a great technology to be able to quantify that. And not just, you know, have a qualitative binary answer. So we get involved with those kinds of projects on a fairly regular basis.
Great, thank you, Patrick. Now our next audience question, how does tracer distribute equally in reservoir?
Okay, Ivy, I'm going to grab this one too. And, you know, as far as the application of tracer, I kind of discussed the physical forms, right? You have to use the right physical form. When you talk about doing an interwell study, and Mariano, maybe you can expand upon this, but from an operational perspective, it's typically done as a pulse injection, and it moves with that frontal wave, versus continuous injection that can be utilized to have a fixed concentration over the total volume. So if you have a known injection rate, you can trace an entire volume with steady state or matching rate like we do with stimulations. But it's really going to be the transport mechanism that drives how it moves through the formation. We can apply it as a continuous injection to look at communication and recovery, or as a pulse during interwell type programs. Mariano, I don't know if you want to add anything to that or not.
No, I think that was very clear, Pat. Perfect.
Great, thank you. Our next question, what kind of pieces of information do you request from clients that would help you design a customized tracer solution for them?
Mike, would you like to answer this one?
Sure. Some of the basic things is, you know, on the well is how many stages. Need to know a bottom hole temperature. We've got to know. We need to know what you're trying to achieve. Number one, are you trying to just get toe confirmation? Are you trying to understand really what's going on along the lateral? Are you trying to figure out where do I want to land this lateral? A lot of people are pumping slick water, and a lot of people, there's some misunderstanding on the carrying of sand and slick water. You're not going to push sand up when you create a frac slick water, gravity. When it goes out the perforations, it will go down. It's basically a one centipoise fluid, and it falls down the bottom of the fracture. So it's very important where you place that lateral. So I need to understand your objectives of what you're doing. So we need to know that your frac schedule is basically a volume to determine how much tracer we're going to put in there. But the main thing is we need to understand what you're trying to accomplish. And there's a lot of uses that as a guy who's sat on a bunch of frac jobs, I just want to talk about like shales. Shales, you get into periods where everybody wants to pump 100 barrels a minute or something around that. You'll get into stage, say a third of the way into the lateral, and all of a sudden you're down to 50 or 60 barrels a minute at your max pressure because you're running into something. Is it a ductile shale? Is it you're drilling out a zone? And so you could save yourself a ton of money if it's just you run into this all the time. Are you wasting money trying to put all your sand into that interval? And so the only way you can determine that is put tracers into this. If you're seeing this happen over and over again, if you're not producing hardly anything out of zone, why put all the sand into it? And so if you run into it all the time, trace it, see what's going on. But there's so many different uses that we've got for tracers. I need to understand your objective. Pat, you got anything else I've missed here?
Yeah, I think one of the things that's really important to know about a project is those goals and objectives. And then there's a few wellbore parameters that really stand out to me. Well temperature. Some of the higher well temperatures are going to require, specific tracers that have been tested to those temperatures that'll survive that reservoir environment for decades, where they don't experience thermal degradation and things like that. So, we've spent a lot of time and effort making sure that we've done the research and development ahead of time before doing projects. So we're very well familiar with the things that may or may not impact the suitability of particular tracers in their phase. So that part of it's pretty important. Volumes is another one, and how that relates to good goals and objectives. So those are the primary things I would say is your dilution volumes, temperatures, and then making sure that the program and physical forms of tracers that are used are suitable for the investigation and learnings that you're trying to achieve. So that's how I'd answer that one.
I'd say one other thing I noticed in the chat. There was something on are there gas tracers? So there's water, oil, and gas tracers. I don't know if y'all were going to ask that question, but Pat, you might cover that on what's available.
You bet. Depending on what the circumstances are, there's a number of gas tracers available. What we want to make sure is that we're using gas tracers that represent the gases in the reservoir, their travel. And fortunate, we've got a research and development team that has 4 decades of experience analyzing tracer behavior, core, phase behavior, pressure, all of those things. So you bet we definitely do quite a bit of gas tracing and understanding gas production from unconventional wells, as well as gas transient from injection to producers.
Thank you all for such in-depth responses. That brings me to our next audience question. In unconventional reservoirs with multi-stage hydraulic fracturing like the Wolfcamp A, based on your data out of 50 stages, how many stages produce the majority of production?
I guess I'll get that one, Ivy. I think it's a great question. Stage production and stage variability along a lateral is going to have so many different things that impact it, from what's the fluid systems being used. Are they different along the lateral? Will they clean up different? Where is the wellbore in the pay? And what kind of fracture barriers are there along the way? When it comes to longer laterals, you know, I could say that 1-2 mile laterals, we generally see fairly even contribution along a wellbore over time. Now that we're getting into 4 mile plus laterals, we have some example wells that we've done. I'd like to see that data set build over time to know that we're actually getting that contribution over that longer distance. But geology really plays a massive has a massive impact on how the well produces and how stages produce, as well as the parent wells. So for me to say out of 50 stages, 30 produce, I can't provide a concrete answer like that. It's really going to be based on wellbore placement, and the geology that it crosses over the lateral.
Okay, great, thank you. And our next question, if you're ready, is would chemical treatment for wax, hydrate, or asphaltenes in the Permian or other unconventional assets require any special considerations during screening as compared to conventional fields?
Let's see. Ivy, you're going to have to repeat that one for me.
Sure, yeah, it was kind of a long one. Would chemical treatment for wax, hydrate, or asphaltenes in the Permian or other unconventional assets require any special considerations during screening as compared to conventional fields?
So if we're referring to the tracer materials being used versus conventional fields, the tracer materials that we use all have very, very strict criteria for their phase-specific nature. So would I have to use a different tracer for a heavy oil versus a light oil in an unconventional field? No, they're all being applied in solution at the under the same conditions in the wellbore. Now, if I were to use a solid material tracer, I may want to consider a different formulation under different circumstances to increase longevity, because a solid tracer is going to be 100% reliant on its chemical characteristics and its affinity for that particular oil phase, API, if you will. So solid materials, definitely want to look at what is the formulation and which ones are being used to create longevity. And really, we're pretty lucky to have the research and development group that we have, as they're constantly working on those kinds of things. We've been doing solid tracing for 30 years, in flow tracing with solids. So we have that experience. But as far as applications for stimulation, due to the chemical characteristics of the hydrocarbon tracers that we're using and the application methodology, no, I wouldn't make any changes.
I want to touch something else on that, and that additives to frac fluids, I don't know of any of them that affect negatively a tracer, like scale inhibitors, biocides, clay control, surfactants, cross-linkers, breakers. I've never run across any of that. I mean, that's all been tested. I don't know of any issues of running any of our tracers into any of those type of fluids.
Okay, thank you guys. So we're going to take one final question from the audience before we start to wrap up. This audience member would like to know, how to overcome uncertainty caused by crossflow between zones when using tracers in wells.
Well, that's a really good question. I'm going to let Mariano finish that question out, but I'll start it with crossflow is something that does occur. If we're talking about crossflow in stimulated wells, you know, we're often used to identify water production, manage water production along laterals where sleeves are closed. In vertical wells, when there's concerns about a lower water producing zone or upper water producing zone, we can identify if it's actually communication behind pipe that's causing the issue. Now, when it comes to inflow tracers, that's a little bit trickier as far as dealing with crossflow. And I know that our data team commonly identifies crossflow looking at the return curves during transient study conditions. So that's something that they focus on considerably, and they can notice and identify potential crossflow in the return curves that they're seeing during transient study applications. So Mariano, as far as inflow tracers and crossflow, is there anything that you want to add to that?
No. Obviously, it all also depends on the length of the well, types of formations that it's going through, types of rock. There's obviously different conditions and different well completions, so it could vary very much. But going back maybe to more of the conventional vertical wells there, also, I think it's very important, or a lot of our clients always want to understand also if, you know, if there is crossflow, is it going to, you know, top layers where there's maybe, you know, sweet water or drinking water that is communicated to the surface, and if there's any part of the well that's connected to that zone. So it's very easy to detect, and there's very different variables why sometimes people need to understand the crossflow. So I think that's pretty much it.
Great, thank you all. So that concludes our Q&A session and today's webcast. We'd like to thank you all for attending. We'd also like to thank TracerCo for putting together this timely and informative presentation. And finally, an on-demand version of the webcast will be made available in the coming days and will be emailed to everyone. Thank you all.